కొద్దిగా చిన్న అన్నట్టు మీరే కనుక్కొని చెప్పలేదు ఇంకా మాకు. I think it is saying I have a problem with the video. My side బాగానే ఉంటుంది. Yeah. You can సార్ వాళ్ళు కనిపిస్తున్నారు. ఒక 3 minutes లో స్టార్ట్ చేస్తామని చెప్పన్నారు. ఓకేనా? అన్నా నువ్వు స్టాప్ స్ట్రీమింగ్ చేయలేదు కదా, అది చెయ్యాలన్నా, అది చేయకపోతే ఆగదు.
అంటే maybe he's changing the laptop or something like that.
YouTube live ఇచ్చారు. మెయిన్ ప్రాబ్లం అక్కడ ఈసారి ప్రాబ్లం ఉంది. చెప్పండి చేసి వాళ్ళకి
చెప్తాను చూస్తున్నాను. ఎంతమంది అయ్యారు? గుడ్ మార్నింగ్ ladies and gentlemen. Seems that there is a technical snag on the speaker's end. He is trying to rectify it, and I hope Vijay will be soon be on line. Hello. అవును, ప్రాబ్లం ఉంది దానికి మళ్ళీ జాయిన్ అవుతానని చెప్పి వెళ్ళిపోయాడు. ఓకే, వన్ సైడ్ ఏం ప్రాబ్లం లేదు, వన్ సైడ్. ఓకే, అక్కడే ఉంది.
రాలేదు.
ఏం చేస్తున్నాం అసలు ఆ కళ్యాణానికి? అది వాట్సాప్లో చేయొచ్చు కదా, ఆలోచిస్తున్నాను. ప్రాబ్లం కాదు, ఫోన్ చేసి బాగుంది కొన్ని యూట్యూబ్లో అవ్వచ్చు అన్నాడు. యూట్యూబ్లో ఆయన మాట్లాడేస్తాను, అలా మాట్లాడడం లేదు యూట్యూబ్లో కదా. సార్ Vijay.
Yes, sir. Sorry, there is some technical difficulty here.
Yeah.
Can you see me now?
Yeah. Yes. Yes.
Yeah. Thank you.
Right.
Vijay, good evening.
Good evening. Good morning, Master.
Okay. Good morning, ladies and gentlemen. I'm privileged to introduce to you Dr. Vijay Tallaparagada, who is the Chief Modeling and Data Assimilation Branch and also a proud alumnus of our Department of Meteorology and Oceanography, Andhra University. Vijay did his MSc from Andhra University with a gold medal, and then he later pursued his MTech in Atmospheric Science at the Department of Meteorology and Oceanography, and then he has been a CSIR Senior Research Fellow for finishing his PhD, and he did his PhD jointly at Andhra University and also at the Florida State University under the tutelage of the very famous Professor T.N. Krishnamurthy, a renowned tropical meteorologist. After that, he joined the NCEP as a hurricane team leader, and he has been in that position from 2006 to 2015. Vijay has been a chief of the Global Climate and Weather Modeling branch, and right now he is serving the NCEP as a chief modeling and data assimilation branch. He has got 2 gold medals, one recently for the development and accelerated implementation of the NOAA's flagship model GFS, a foundation for the FP3 based on the unified forecasting system. Vijay had many international publications and is known worldwide for his research on WRF and tropical cyclones. And with these few words, I now request Dr. Vijay to deliver his lecture for the benefit of the students of Andhra University mainly. Vijay, please.
Yeah. Thank you. Thank you, Professor Ramakrishna Garu, and congratulations to Dr. Naidu Garu for becoming the chairman of the department. It's a pleasure to be here virtually, although usually I come during this time to India, but this year, because of this COVID situation, all travel was closed and we're all working from home. So it's still very exciting to have this opportunity to speak to you all, share some of the work that we are doing at NCEP, and provide some opportunities on how you can engage in advancing your knowledge and your enthusiasm in numerical weather prediction or any other topics that you are interested in. There are wealth of opportunities available both in research and in operations. And I would like to offer a perspective from the National Centers for Environmental Prediction, or NCEP, where I work for. And we are recently advancing our capabilities by modernizing our weather prediction systems for operations. And we're also developing the systems for research so that there is a community who can participate in this development process, and we call it Unified Forecast System. This is very similar to the integrated forecast system that European Center has been running for a while, and the UK Met Office in London and in Reading, they also have a unified model that India is using at NCEP. Very similar to that, we wanted to advance our technologies in such a way that there is a framework to conduct operations and research in the same way, such that we can have benefit of transitioning research into operations for practical applications. So I will try to provide some background on what we do, and then go into some details on what this unified forecast system is and how we have been advancing that. So as I mentioned, I work for National Weather Service in the United States, and our vision and mission are to build a weather-ready nation where a society is prepared for a response to weather-dependent events. In US, weather is a multi-billion-dollar business. It is not just for public lives and safety of lives and property, but also for economic development. And there is a lot of private industry, government sector, defense, all depend on the weather forecasts. And Weather Service is officially responsible for providing the data or the model guidance that we provide for water, weather, and climate provides basis for warnings and watches, not only for the United States, but all the territorial adjacent waters, ocean areas. The data and products form a national information database and infrastructure which can be used by other government agencies, public sector, private sector, academic sector, and the whole global community. And as a matter of fact, NCEP is the only center that provides all the data free of cost, on time, every time in real time. So that's something that we take pride in. We are a major WMO center for data distribution. All the developing countries and underdeveloped countries, they all dependent on the data that we provide for their regional applications. So I just wanted to give you a brief introduction on what a numerical model is and also what a forecast is. Forecasts are made by people. Models don't do forecasts. They are done by people in India Meteorological Department, people sitting in cyclone warning centers, or weather forecast offices in US. The service centers within our NCEP also provide forecasts for certain aspects like the hurricanes or severe weather. Models provide guidance. There are numerical models that are foundational to do these predictions, and that is considered as a guidance that the forecasters or the people use it. And a prediction is now inherently linked to numerical models, either statistical models or statistical dynamical models or full three-dimensional models. Most of these models are run at the center where I work for. There are more than 20 systems, about 1,600 kind of codes and scripts, billions of data that we ingest daily, and millions of products delivered. And we share our data with worldwide partners, including the Department of Defense, European Center, UK Met Office, Japanese, IMD, and so on and so forth. So this is kind of a big enterprise that we are engaged in. There are emerging requirements that we have to continuously follow. The requirements are the weather-ready nation. For instance, everybody should be prepared for the weather, high impact events, weather to climate, like the seamless suite of guidance and products, not only for short range, but seasonal to subseasonal to interannual scales. We are continuously advancing our observing systems, and all these NWP models are heavily dependent on high performance computing, and we invest in supercomputers to do the model development as well as the operations. Data dissemination is a big enterprise by itself, and we have the guidance systems that use the data assimilation, modeling, ensembles, post-processing techniques, and we touch a little bit on the predictability by providing the probabilistic forecast for instance, the convective systems or the subseasonal to seasonal or longer timescales. So this is kind of a scope of all our applications here, spanning weather and climate. And as you can see in this diagram, we provide guidance that meets the forecaster's needs from minutes all the way to years. And the benefits reach multiple sectors like life and property, all the way to ecosystems and environment and health, fire weather, commerce, energy planning, hydropower, everything that touches the weather in our daily lives. The forecast products itself look like the warnings and alert coordination, watches, threat assessments, guidance, and outlook as we increase in the timescales. And the names that you are seeing here are multiple forecast systems that we use for various applications. And as you can see, there are so many models that we are running here for different applications, and they are growing too much that we cannot manage them or maintain them at the same level of sophistication that is expected from these NWP systems. So that is the scope of my talk. In the next half an hour or so, I'll be talking about how we are going to consolidate all these different models, including the global forecast system, the GFS, that many people are aware of, and the global ensemble forecast system, the GEFS. And we have the hurricane models, we have regional models, and all these models are using different dynamical cores, different physics, different data assimilation techniques, and it is obviously impossible to manage all of them with limited support and resources that we have. In a nutshell, this is kind of a busy diagram, but this is how we operate in NCEP. These are all models intertwined. That means if you change something that will impact somewhere else. So you need to be very careful in how you design the systems in such a way that they're all seamlessly operating. And the global systems here are the major systems that we provide for medium range and seasonal to subseasonal scales, the CFS, the GFS, and the Global Ensemble Forecast System, the GEFS. We have multiple regional models. We have space weather, we have short range ensembles, we have the regional weather applications, hurricane models, wave models, ocean models, ecosystem, air quality, and then several data assimilation systems that go with all these modeling systems. So what we wanted to do is from moving from this quilt of multiple models into a single model or single framework that supports all these applications, from analysis all the way to seasonal forecasts. It can have the hurricanes, it can have the whole atmosphere for space weather. It also can drive the hydrology model. And the application here is now considered as the UFS, the Unified Forecast System. And the product is a coupled ensemble that also comes with the reanalysis and reforecast, because we need to understand the model behavior and validate and calibrate using these reforecasts. So this is how we are trying to develop our next generation modeling system. So the Unified Forecast System, it is not just developed at NCEP. It is a community-based, coupled, comprehensive modeling system. It can be configured into multiple applications that can span from local to global domains, and it can provide the predictive timescales from sub-hourly analysis to seasonal or interannual predictions. And it is supposed to support both the weather enterprise and also the research components of the community. So one of the goals of the activity is to improve the interface between the research and operations. That's how we wanted to develop this system. And now, instead of having models, we are creating applications. These applications are all using UFS, the medium range weather, the subseasonal to seasonal, hurricane application, the short range weather application, space weather application, marine and cryosphere for ocean and ice, coastal application, air quality for aerosols and atmospheric composition. So these are the main applications that we are developing using the common framework. And it's a hierarchical system development. How we develop these models is pretty intensive in terms of designing the system and conducting a lot of studies that prove that these are working as expected. So we have focus studies like great insight into the detailed behavior, impact on application performance, and those are using the hierarchical system development. That way we ensure that all these meet our standards, not only for software, but also for scientific integrity. So how do we get that? You know, if you really think of a lot of ideas that are generated in the community, like, you know, many people work on either data assimilation or physics or dynamics or process level understanding. There are so many things that are developed outside of weather service or what we can accomplish in a single center. And we need to have a process in which these elements can be integrated. And what we do is we provide a stage and gate process. These are the gates. At each gate, we have certain criteria that they need to pass or meet the requirements so that they can go into the next stage, and then the next stage eventually land into operational space. If they miss any of these gates, they go back and then try again. So that's how this stage and gate process works, so that you know, all the developments have a fair chance of contributing towards collective improvement of UFS applications. So how do we get that? You need to have a framework. You need to have a system that can support all these developments. And many people probably are aware of the models that are currently available, like the WRF. I hope many of you are aware of it and are already using it. It's a very well-supported system. Very similar to that, we are developing this UFS as a community model. And we developed certain system components that are essential for integrating the data assimilation, the Earth system components, and the physics in a single system. So we divided these tasks into 7 major areas. One is the coupling components, all the Earth system components like the atmosphere, ocean, ice, waves, aerosols, land. They're all connected using a mediator, which is a powerful software that transfers data from one component to another component without needing to read and write the output. So this is happening all in the memory. Interoperable atmospheric physics. This is an important component of the modeling system. And as we develop physics for certain applications like global or regional or hurricane, they all need to work together. And we created a framework called Common Community Physics Package Framework. And that is considered the next generation physics development for atmospheric modeling systems. We need a workflow. We need to have something that people can easily use and also develop. So we call it a community-friendly workflow so that people can do experiments, case studies, or fully cycled systems. So that's another area that we are advancing. And then, as I mentioned, hierarchical model development capabilities so that we can do a lot of testing in a very carefully designed way. We also need a better verification for evaluating our model results. And we are using a toolkit called MET, the Meteorological Evaluation Toolkit. It is another powerful verification tool that provides you standard way of evaluating model results. This is all software engineering, and we need very careful repository management. We are using Git and GitHub, which is open source. Anybody can go and develop and share all the developments with the rest of the community. And we also need to have the developer support. And all these are considered the shared community infrastructure that allows us to develop this UFS. And I will then talk about the dynamical core. The dynamical core is like the engine of NWP models. If you think of a model is consisting of the dynamic core, the physics, and the initial conditions. These are essential for running a numerical model. And dynamics obviously is the most critical. This is the 3-dimensional model that resolves the diabatic motions and then connects the physics to the moist processes. So we chose the finite volume cube sphere dynamic core as the center for all our UFS applications for weather. So this is how the cube sphere grid looks like. You might have already learned about various types of grids, the regular lat-long grids, the Mercator grids, the polar stereographic grids. You have C grid, D grid, you have A grid, Arakawa A grid, Arakawa B grid. These are all various ways to dissect our Earth atmosphere system. And each have their own advantages and disadvantages. Most of these models suffer from polar problem because the meridians all converge at the poles, creating singularities. And so we need to be creative in identifying how the grid can be resolved without having to have those singularities. The spectral models were good until the last decade, but they are not scalable. They are hydrostatic, and as we need higher and higher resolution, we need to go into non-hydrostatic scales, and also those grids that can be run on massively parallel computer systems. And this cube sphere grid allows us to provide higher resolution, allows for more uniform grid structure. It's a mnemonic cube sphere. It's a non-orthogonal. Instead of using numeric metric terms, we use covariant and contravariant winds. The fluxes and the winds are defined at the interface as well as at the center points, as you can see in this diagram here. And the kinetic energy is just half of the product of those C grid and D grid winds. And since they are defined in the local coordinate, in order to get U and V, you need to rotate those winds to get zonal and meridional components of the winds. But that can be done without much of a problem. But these solutions are much more conservative. the mass and momentum are all conserved in these numerical models, and they provide us the capabilities to provide finer resolution where we need it. It's also Lagrangian dynamics, except that it is Eulerian in horizontal, Lagrangian in the vertical. That means the vertical coordinate actually moves with each time step based on topography, based on the pressure differential. The prognostic variables here are the UV on the D grid, the vertical velocity W, and then the Q, del Z, del P, and theta V. These are the moisture variables. All variables are layer means. There is no vertical staggering. We use the piecewise parabolic method for finite volume numerics. It's positive monotonic. That means there is no noise or too much diffusion. We also use finite volume advection, very conservative. This is developed by S.J. Lin and Ricky Rood, very famous dynamic core developers. We also have subcycling tracer advection. That means you can do a dynamics time step different from physics time step in such a way that the tracers can be cycled within those dynamic time steps. The discretization is also time-centered, and so we get exact computation of the absolute vorticity. There are no approximations here. So how does it reflect in actual workings? I mean, why do we need such a highly conservative properties here? And the rotation is an important component of this dynamical core. As you can see, this is the polar vortex here. These are dust storms and hurricanes. This is the inner core of a hurricane here, or a tornado cell. And this is another highly intense hurricane near Mexico. All these are rotational flows. That means you need to pay extra attention to potential vorticity that need to be highly conservative. And the FE3 dynamic core really addresses that problem by providing higher order numerics to resolve these vorticity features. This is an example of how the cloud microphysics and the dynamic core are working together. This is a simulation from the global modeling system using the FE3 dynamic core. And these clouds are actually representing the moisture fields from the model itself. This is not a satellite imagery. It is a model produced water vapor. And you can see how realistic the simulations are in terms of resolving various features, both over continents and also over the oceans. And this is something that the GFDL, the Geophysical Fluid Dynamics Laboratory, has developed and advanced it for climate purposes, but now we are adopting it for weather prediction. So the cloud microphysics is an important aspect of the model, and I'm just trying to compare here what we have in the FE3 GFS compared to, say, the ECMWF model. We use the 6 species cloud microphysics here compared to 5 species ECMWF scheme. We try to resolve more of the water vapor and various hydrometeors like the cloud ice, cloud water, rain, hail, and snow. Unlike the bulk microphysics schemes like what European Center uses, we try to address majority of these interactions between these hydrometeors, and that's something that has advanced our forecast skill rather significantly. And it can be expanded into double moment scheme as well, but right now it is still a single moment scheme, like there is no number concentration or density of these hydrometeors considered. It is still a fraction of the water vapor that goes into various partitions based on the properties. And but the microphysics is directly connected to the dynamics, such that the advection and the hydrometeors, they all happen, interactions happen at the same time. So this is another way of demonstrating the impact of cloud microphysics in a global model simulation. This is a kind of a 6.5 kilometer resolution model globally, and no parameterized convection. It's all explicitly resolved. And again, you can see how realistic these features are the model is pretty stable. It was running for something like a 10-day forecast here, and it produces more realistic atmospheric features out to 10 days and still behave very stable and efficient. And this is a part of the Diamond project that we recently demonstrated the capabilities of this model running at much higher resolution. So using that, we started transitioning our global models using the UFS, which is the finite volume cube sphere based UFS, medium range weather forecast system. The initial implementation that went in last year in June, that's the one that we recently were awarded a gold medal from Department of Commerce. This is still working at a 13-kilometer resolution, not as high as 6.5 that you saw. Because of the computational constraints, we had to limit it to 13 kilometers. However, it has 64 layers in the vertical, going to 54-kilometer top. The data assimilation system uses 80-member ensembles. We provide uniform resolution out to 16-day forecasts. As I said, it's a FE3 non-hydrostatic. And the physics is the GFS physics with the GFDL microphysics. And there are several benefits that were noted in the evaluation period, like we improved the anomaly correlation at 500 millibar. That means the general forecast skill from the model has significantly improved. And there are other improvements like the tropical cyclone track and intensity, warm season diurnal cycle of the precipitation, improved downstream models, extratropical cyclones, precipitation scores, reduced biases. So these are all kind of evaluation metrics that we use to demonstrate how the model is performing compared to its previous version. Likewise, we are making another major upgrade, which is going to be implemented in another 2 months. Actually, on February 3rd, 2021, we are raising the model top to 127 levels, 64 to 127, and also raising the model top from 55 to 80 kilometers. Advanced physics is included. We coupled now this atmospheric model with the wave model. The global land data assimilation system is introduced here. We use a 4-dimensional incremental analysis update. This is a new technique that was developed at System Research Laboratory in USA, which is kind of a 4D war, but not necessarily using an adjoint. It nudges the analysis on an hourly basis in a 6-hour increments, and it uses the stochastic perturbations to provide the initial condition uncertainty. We also have new satellite data sets that are going to be implemented in terms of data assimilation. And as you can see, evaluation is a critical component of all these model upgrades. We carefully evaluate our models before they go into operations. And some of the highlights for V16 that's going to be implemented in February is that we had some cold bias in the winter season in the previous version. Now we mitigated that. Less skillful track forecast for the stronger storms. We improved it. Tropospheric, stratospheric temperature forecasts have improved, and also precipitation biases for moderate rainfall also have improved. So these are kind of highlights of global NWP, because these models are used for decision-making purpose, and continuous advancements are essential. For those who want to know how this model is run in operations, these components here are initialization steps, including data assimilation. As I mentioned, we included the global wave model for the first time in our operations, and the ENKF or LETKF is applying the ensemble-based covariances for the data assimilation, and then the forecasts are done once the global data assimilation system provides the analysis. The GFS is run and it's forecast. It runs 4 cycles a day, 6Z, 6Z, 12Z, 18Z, and 0Z, and provides 16-day forecasts each cycle. We also made a significant advancement by moving the ensemble system into the same framework, the UFS framework, and also uses the same FE3 dynamic core. Since it is an ensemble system, we cannot run at a higher resolution. We are running it at 25-kilometer resolution. It has 31 members, and instead of 16 days, we send the forecast data out to 35 days. That means the weather forecasts are now available 1 month in advance. They're not as good as what we can get, say, for a 10-day forecast, but there are several users who want to know how these models perform, especially the uncertainty information that we demonstrate using the spread of the ensembles. Like this is one hurricane that was hitting in 2018 in North Carolina. And you can see the range of solutions about 10 days before its landfall. It can go anywhere south of Florida all the way to Maine or in Canadian borders. But the colors indicate the probability here. The red colors means highest probability. The blue colors means lowest probability. But still, there is certain information that's available in these ensemble systems that people can take advantage of in terms of making emergency preparations. Again, it's a global model coupled to waves and also quality. They are all combined into this ensemble system. We have a 20-year reanalysis and 30-year reforecast data that came with this implementation. That's a great research tool for people to evaluate. The NCEP reanalysis data is heavily used in our literature. We can now say that this 20-year reanalysis is much more skillful and more modern. It uses all the available data sets in the last 20 years. And we also have the 30-year reforecast data that we can study for model biases, understanding the model biases, and improving model performance. So the Earth system component for NWP is kind of an emerging science here. It's both a science and an art. The Earth and atmosphere, they're all seamless. We don't necessarily break them down into pieces except for our convenience. In the nature, they're all working together. But in NWP, so far, there is a strong bias towards either using atmospheric models only for weather prediction or ocean models only for ocean prediction. And the interfaces are generally fixed, like the atmospheric model always is given constant SST, even though we know that SSTs change, the sea surface temperatures change. So things have changed in the past decade or so in identifying a best way to couple all the Earth system components in a single framework in such a way that we can replicate the nature in a more consistent way. And so as you can see here, the dynamic core, the physics, they are all coupled using this mediator to the chemistry, the land, the waves, the ocean, sea ice, air quality, hydrology, coastal waves, surge models. They're all coupled in the same system such that you can selectively use them for various applications. You can derive the GFS application or the GEFS application or any other applications that are surrounding here. So these are kind of a new way of developing things that I will illustrate a little bit more. For instance, we want to create GFS. Since I'm not worried about ocean models yet, or ocean or ice models, I don't need to use them, but I need the wave watch, which is the wave model, the land model, the physics, dynamic core, the infrastructure, the IO, the mediator. These are all selected for the medium range weather forecast application. You don't need the space weather or chemistry for this component. So that allows us to configure the UFS in such a way that you can selectively determine what components are needed for each application and use them accordingly. If you think of the ensemble system, the only difference between the medium range and the ensemble system is that now we have ocean, ice, and chemistry also added compared to the previous one. So you can increase the complexity of the systems or optimize the system in such a way that it provides you the best forecast. So in order to continue advancing the system, we created a new project called the UFS project. It's a community-based coupled modeling system that is actually going to be operational by 2024. And I'm leading this project right now at NCEP. And this is the largest investment in this UFS, about $13 million per year for 2 years. It's managed both by Weather Service and research. We have about 100 scientists working in this project from various divisions of NOAA, universities, and outside organizations. I'll skip this, but I'll just say that this is a new way of doing business. We are doing an experiment to carry out the research and development in a collaborative project, but the ultimate aim is to improve the operations. And we are engaging with wider community with a dedicated funding, but there is always a room for allowing interested or engaged or willing participants to work with us in a single management framework. We have a 5-year vision, but since this project is funded for 2 years, we have determined the deliverables for the first 2 years. We also want to highlight the scientific priorities as a basis for improving these models. We're not just developing these models for the sake of NWP or increasing the complexity of the systems. There are some known problems that are identified in the literature. Many people are looking at all these operational models for a long period of time. They have documented, for instance, the coupled model, the CFS, has several biases. The key modes of variability like MJO and so, we're still struggling to predict them adequately. Data assimilation system is still component-based. We have not gone into the coupled system for data assimilation. We don't have a convective allowing ensemble forecast capability. We want to improve the initialization for all scales, convective all the way to global, by using all available observations. And we also want to improve the quantification of model uncertainty in ensembles, especially near the component interfaces. So these are the basic priorities for developing the UFS going forward. And so we created this project with myself, Jim Kinter from George Mason University, and Jeff Whitaker from NOAA Earth System Research Laboratory. We three formed the team for the UFS R2O leadership, and we have multiple teams under us, like the medium range and sub-seasonal to seasonal forecasts, the short range weather or convective allowing models, and then the cross-cutting infrastructure. And under these teams, there are sub-projects focusing on specific components like the data assimilation, coupled model, physics, air quality, atmospheric composition, real-time mesoscale analysis, rapid refresh forecast system, hurricanes, warn-on forecasts, and we have the infrastructure support for both modeling and verification post-processing. So this is a kind of a very aggressive way of doing the model development, but in a very consistent way in order to accomplish what we would like to see. So we already developed this medium range weather to sub-seasonal to seasonal system. It has 6 components. The atmosphere, as I mentioned, is the FE3-based dynamic core with GFS physics. The ocean, we have chosen the MOM6, the modular ocean model. It's currently running at a 1/4 degree tripolar grid with 75 hybrid levels. We have WaveWatch 3 for wave models, and the CI6, Los Alamos sea ice model for ice. NOAA-MP for the land model, which is also available in the WRF. Atmospheric composition comes from GOCART, developed at NASA. And we have a mediator to couple all these 6 components. And this is how the new seasonal forecast system looks like. And the plan is to implement it in 2025. In the next 4 years, we'll be working on that. We're already seeing some improvement in the skill from the new UFS. We are developing this UFS systematically, and the recent version of the sub-seasonal forecast system has actually twice the skill compared to the CFS. This is the anomaly correlation score for weeks 3 and 4 for temperature, and this is like 100% improvement in the skill. And compared to, say, the global ensemble system, this single deterministic system has much better skill, and that's pretty positive in terms of how we are advancing the model. The data assimilation is a critical component here. We are developing this just like the algorithms that are available in NCAR for data assimilation. We are using similar approach, but a more modern framework developed by Joint Center for Satellite Data Assimilation. We call it JEDI, the Joint Effort for Data Assimilation Integration. We have multiple algorithms that are currently available, the 4D-VAR, the 3D-VAR, and the ensemble variational system. And it's already effective and functional. I'll provide more details in a later slide. And as I mentioned, workflow is a critical component. The cross-cutting infrastructure team has developed this workflow such that it is modular. The user needs to only interface him or her here at the workflow manager level. All others are configurable using a configuration manager, and the components are selected based on what configuration people would like to use. And it's pretty effective in separating the concerns, but developing in a community framework. The regional applications are of interest to us. Using the same global model, we now have developed a regional model so that we can develop a capability that's more convenient for use, low computational overhead, ideal for people with limited resources. It's simple and easy for short-term forecasts. You can provide very high resolution. We can provide a 1 kilometer grid or even sub-kilometer grids. And 3 kilometers is not necessarily the end because we wanted to go into the LES or the large eddy simulations, urban scale or Warner forecast or the turbulence. So there is new opportunities that are going to be provided when you have these regional models. And I'll show the difference between the WRF and the FE3 based regional or limited area model capability. The limited area model is actually kind of another tile on the same face of the cube. And we use the same mnemonic projections. It still can be done as a nest within the global model. If you want to really work on a global model with a high resolution where you need it, you can create a setup in such a way that the global model can run with a 3 kilometer regional resolution, high resolution grid. And what we did is we separated this tile 7 as a single model so that it can provide the limited area capability. Just like what you're seeing here, this red box is the domain for the regional systems for the United States. We have the model already available. There is also support for this application that's available so that people can exercise it. There are people who are already using it in some Asian countries using the same framework. And that's something that I would like you guys to experiment if you are interested in. I'll show how you can do that. So the original GFDL grid, the FE3 grid, has even though we call it 3 kilometer grid, it definitely is not 3 kilometer everywhere because the way the grid transformations work. And the ARW, for instance, the one that you guys are using for WRF, has a similar problem. As you go poleward, the resolution can degrade. And so we created a new grid called the JP grid or Jim Purcell grid, which stretches these grids into a much more uniform grid spacing throughout the domain. And so this is something that's required to provide constant resolution for resolving the features everywhere in the domain. And this is one of the greatest advantages of the FE3 based regional model. We have 2 different physics options currently available right now. The microphysics can be either Thomson or the GFDL microphysics. The PBL is the GFS PBL or eddy diffusivity mass flux scheme, or the MYNN or Miller-Yamada neural network based PBL. All other schemes like the deep convection is the SAS or the simplified Arakawa-Schubert scheme. Radiation comes from RRTM, the rapid refresh, the radiative transfer model. unified gravity wave drag, NOAA land surface, and NOAA MP, and then other standard parameterization schemes that are needed for representing ozone and water vapor. This model is actually much easy to run. You can run it on your MacBook, you can run it on your Ubuntu or Red Hat Linux boxes. We have limited test platform cases that are available, and it can be built on any GNU platform or even on the cloud. So there are 4 levels of support that are being provided to run this model. There's a lot of support available for running this model, as well as community interactions through a forum. I'll share these slides with you guys to go through and see what excites you guys. But our goal as an operational center is to develop an application, and we call it a rapid refresh forecast system. It's kind of an ensemble system for severe weather prediction, and it will have a convective scale ensemble data simulation system. So the way we are advertising this is that anybody who is working on it finds a problem, reports to us, we will fix it and move forward. That's how the collaborative development works. But in that process, we are also feeding it back to the research community so that they can do interesting case studies and also publish papers, or can be part of your thesis work, or write a journal article. There are so many things that we can do with the community support. I'm also still working on the hurricane modeling. I was initially starting my career at NCEP as a hurricane model developer, and then hurricane team lead. We operate the operational HWARP, the Hurricane Weather Research and Forecast System. That's, again, another collaborative project that I was leading in the last 10 years. We are currently operating this model at a 1.5 kilometer resolution. This is an example of last year's Hurricane Dorian. This is an ocean and wave coupled system. What is important here is to represent the ocean interactions on atmospheric processes, especially for tropical cyclones. They are heavily influenced by the cold wake generated by the oceans. So our specialization is to do these forecasts in real time operationally. These are not research models, these are operational models, but we can use them for research as well without sacrificing any quality or quantity of these developments here. And actually, IMD runs a version of HWARP for operations in India, and that's coupled to HICOM model, and it uses very same technology for predicting tropical cyclones in India. So transforming this from the WRF framework to FE3 framework, how do we do that? So we started this collaborative project again in the UFS framework, and now we have to define the regional domain in such a way that it covers most of our area of responsibility, which is the North Atlantic Basin, and also the Eastern Pacific Basin. I'll cover that here. So we created one version called HAFS, the Hurricane Analysis and Forecast System. It's a simple single 3-kilometer domain that covers most of the Atlantic. We also have a grid that's embedded within the global model. We call it HAFS-B, and both are providing very reasonable solutions. Actually, some of these results are much better than what we get from HWARP. So this is something that we're all excited about in terms of moving from the WRF to the FE3-based UFS-based system. So our regional systems going forward will be like the rapid refresh forecast system. We'll be using this white colored domain here that covers majority of our areas, including Puerto Rico, Hawaii. These are all weather service area of responsibilities. Earlier, we had these little boxes that we were using for developing the severe weather forecast applications. We don't need to maintain them anymore. We just have one system running in an ensemble. And similarly, we can provide hurricane forecasts using a single hurricane analysis and forecast system for both Eastern Pacific and Atlantic Basin. So again, using the UFS framework, we are developing these components. The purpose of showing this multiple times is that we are using the same components that are used for the global system or any other application. So that's the beauty of the unified forecast system. It's not a unitary model or unitary application. It can be configured in such a way that you can get what you are really looking for. So some of the early results, as I mentioned, this is Hurricane Michael in 2018. Many models did not capture the rapid intensification. The orange line here is the hurricane analysis and forecast system. We are actually running it at 1.5 kilometers, and that really nailed the intensity forecast. Even the 2-kilometer model is providing the rapid intensification, but it's a delayed mode. So there are evidences that suggest that we need much higher resolution for hurricane intensity forecasts. So 3 kilometers is not sufficient. We need to go much higher, and that we will be working. So we are creating nests within the global model that allows us to provide even much higher resolution, like down to 1 kilometer or higher as needed. So in the next 3 to 5 years, what we will do is we will put these nests anywhere in the world where there are tropical cyclones, so that the products can be directly coming from the global model itself, but with a higher resolution. So this technology is very unique. Only NCEP has this kind of technology for providing high resolution forecasts within the global model. And it's going to be pretty exciting in terms of how the nests can interact, and they also feed back to the general circulation, and the two-way interactions between the hurricanes and tropical circulation is something that we will be looking at in studying it in a more greater detail. So I'll spend the last few minutes on how to get involved, and then I'll take some questions. We have a UFS R2O project, and we have a UFS portal. We have UFS codes and UFS data. UFScommunity.org is the website that's the single source that people can go. It has a lot of webinars, the public release information. There is something called graduate student test. I'll spend a little bit on that. All the development of UFS is happening in an open source. The link is here. The UFS weather model is on GitHub. The data is on cloud as well as the NCEP FTP. As I mentioned, we have the 20-year reanalysis and 30-year reforecast data. Actually, one of our Andhra University students who is currently visiting CPC, Dr. Nageswar Rao, he used this data and started, it was produced only 3 months ago, but he was able to use that data, and now he's ready to submit a manuscript for publication. We also have the GFS analysis and forecasts, along with many other real-time forecast data on the NCEP regular FTP server. So the cloud, it's a free of cost. You can download the data from AWS, Ramajam Web Services. There will be more data that will be provided there in the future. So the graduate student test, what do we expect for a graduate student like you all in this UFS parlance? So what is the GST is how easily a student can get the code, run the code, change it, test it for correct operations, and then evaluate with some standard diagnostic package. You should be able to get the documentation, support, and training, and understand what is needed for the code changes. Like if you find something that need to be transitioned back to operations. So we have different graduate student tests for different applications, but majority of them share the same tasks. So the goal here is for a normal user or normal graduate student, we're not talking about extraordinary or anything special skills. A normal graduate student with some basic knowledge should be able to do all these tasks, the get code, run code, change code, test code, and evaluate all these 5 tasks in less than 6 hours. That is the actual goal, and many people have accomplished it. So we have now the codes, as I mentioned, the repository is available. You have a getting started section that leads you through a quick example. And as I said, it can be configured into multiple applications, but the GST is essentially for students to exercise and inform us how easy it is to use or what can be done to make it even more easier. So one example here is for a subseasonal to seasonal application. Modifying, say, a very simple task, the ocean model within the coupled system. There is a subroutine where you can change it in such a way that you add it by 2 degrees. The ocean temperature, the sea surface temperature, you increase it by 2 degrees and see what happens. Very simple exercise. What happens if the ocean temperature is increased by 2 degrees centigrade? Conceptually, maybe you can imagine it's like a global warming case, right? How do you assess the impact of such a huge change in SST on the model scale or model simulation? It's a thought experiment. It's not necessarily any valid forecast experiment, but it will tell you how to get the codes, compile them, change them in such a way that you are increasing the temperature by 2 degrees, and then rerun the model and see what the difference is produced by this model. So I'm showing you the example here. This is the reference, and you're adding 2 degrees everywhere. This is the difference, the ocean, the difference between this is a 5-day forecast, by the way. The end of the 5-day forecast, you have the warming in red colors and cooling in the blue colors, but you can see more warming in the SSTs by day 5. And this is a precipitation forecast, and the difference in the precipitation is here. And so you can see more precipitation happening or less precipitation happening depending on certain situations that you're looking at. So what it tells you is, this is a way to understand the model behavior or sensitivity of the models to various parameters within the model, and also give a chance to explore or ask questions, scientific questions, on the local impacts of any changes in these variables. So this is a very great tool, and we are extending that to the standalone regional model, the short-range weather application as well. There is a test case. Right now it is still focused on the US extreme weather case, some severe weather example as of last year, June 15th. But the process is the same: get, build, run, and change code, test code for correct operation, evaluate with standard diagnostic package, locate the documentation, support, and training. And you have to be able to do that under 6 hours. And as I mentioned, many people have done that, and you can expand it. You can create a domain for, say, Indian region and repeat this exercise for a case of your interest. So with that, I know I have already taken more time than allocated. So I'll stop here and try to answer any questions. And I would like to invite you to be part of this global enterprise that we are leading here. There are several partners that we are working with. And with your permission, I already included Andhra University as our collaborators with this UFS development.
Yeah, thank you very much, Vijay. We are honored to have added Andhra University on the map of the unified forecasting system. I think now the floor is open to questions. Any questions from the students? Would you like to ask? Vijay, I have a question, Vijay.
Yeah.
This unified forecasting system, how many convection scheme options are there in the unified forecasting system?
So we don't want to add more schemes like what WRF has done. One of the problems with the WRF is you don't know upfront which one to use. And is it scientifically reasonable to develop so many such schemes without really understanding what they are doing? So what we try to do is to only take those schemes that are relevant. So as of now, we have two schemes that are currently supported. One is the Grell-Freitas,
Okay.
the Grell-Freitas convection scheme, and the other one is the simplified Arakawa-Schubert scheme.
Okay. Okay. Thank you. There is a question from Dr. Sujata Patnaik. Vijay, when HWARF is implemented over UFS framework, whether only the grid conversion is implemented for HWARF, and what are the major changes done to work in UFS framework?
So it is completely new model. It's no longer the WRF framework. We are using the FE3 dynamic core, and we are introducing the same technology that HWARF has, like the moving nests, into the FE3. So that is the work that we are currently doing with the support from our colleagues from the OML, like Gopal's team is working with us in developing that capability. So it's completely a new model. It's no longer related to HWARF. We are using the same concepts, but the technology and the tools are completely different from the HWARF.
Okay. There is a question from Pani Murali Krishna. What is the resolution of the data assimilation? Is the UFS and the data assimilation are same?
Yes, UFS uses the same, our data assimilation uses the same UFS models. And for GFS, the data assimilation is done at half the resolution. They're using a 25-kilometer grids to do the ensemble-based data assimilation. That's not a requirement. That's a computational constraint. But otherwise, there is nothing that stops us to do native grid resolution data assimilation. Like the hurricane models or the regional models, they all use the same grid for data assimilation. And we have both the 3D VAR and the 4D VAR and the ensemble variational systems using LETKF and ENKF in our UFS data assimilation capabilities.
Okay. Another question from the same gentleman. Is online aerosol module included in the new version of the model, as a double momentum schemes are already present?
Yes, we have the Go card that provides the aerosol components, including chemistry. Currently, we don't use inline aerosol models for medium range weather applications like the GFS. We still use the aerosol climatology, and the aerosol climatology still interacts with the radiation and convection and microphysics. So it's kind of a 1.5 moment scheme, if you will. But in the future, for the next version, for the subseasonal to seasonal forecast, we wanted to introduce online aerosol feedback directly onto model physics. Both radiation and microphysics will be interacting and be aware of aerosols like the dust and all other constituents of the atmosphere.
Thank you. Any questions? If there are no more questions, let's thank the speaker once again for his elucidating and informative lecture. Vijay, thank you very much. It had been a very long day for you. It should be midnight, past midnight for you. And I thank you very much for delivering this lecture. I think joining me is our head of the department, Dr. C.V. Naidu, whom I request him to propose a vote of thanks to the speaker. Dr. Naidu.
Good morning to all. I thank all the researchers and students who attended the lecture entitled Advanced NWP at NCEP, the Unified Forecasting System for Research and Operations, delivered by Dr. Vijay Talla-Pragada, NCEP, USA. Dr. Vijay is a well-known scientist in the world. He has been publishing high-quality research papers in highly reputed journals. Dr. Vijay won gold medals twice for his best services. No doubt to say that Dr. Vijay inspired so many young scientists. Dr. Vijay, you are our proud alumnus. You were awarded with master's degree in meteorology, M.Tech in atmospheric science, and a doctoral degree from our Department of Meteorology and Oceanography, Andhra University. I personally know that you are a good human being. You are trained under supervision of great legends in the scientific community, Professor D.V. Bhaskar Rao Garu and Professor T.N. Krishnamurthy Garu. I am very happy to see you in the highest position in the scientific world. Your talk has given immense pleasure and new energy to many youngsters to move further into the research field of meteorology and oceanography. Thank you very much for delivering very informative lecture. At present, there are some promising students and research students in our department. I request you to help them in their research career. Thank you, Vijay. Thank you again. Thank you very much.
Thank you for the opportunity, Dr. Naidu. Thank you very much.
Thanks, Vijay. Yeah, thank you.
Bye-bye.
Yeah, you are welcome to India, our department.
Sure, anytime. Thank you.
Vijay, thank you.
Thank you, sir.
Vijay.
Right, Master.
Right, Randy. Right. Thank you. Thank you very much.